Okay, hi guys. So in this video lecture, we'll be continuing on comparing the acidic strengths of organic compounds based on their minus M, minus H, or minus I groups attached, or it can be plus M, plus H, or plus I also. Okay, so let us continue with that. We have to compare the acidic strength of yeah. Okay, between this and between this. So what is the acidic strength? So as you can see here that um, when we make the conjugate base of this acid, there would be a negative charge on this carbon atom, hence, and the same would be for this carbon atom. So we need to compare the acidic strength of this alpha hydrogen over this. So we can see that what is the relative stability order of negative charge on this carbon. So you can see that there is more number of resonating structures that can be derived from this carbon atom, as well as there is more you can say it is serving to both of these minus n groups, while it is serving to only one minus m group. Hence this would be more stable than this, or we can say that this would be more acidic than this. Okay, so just a trend, I'm just writing a trend that uh, we have compounds like carbon, nitrogen, oxygen, fluorine. So acidic strength actually increases along the group. Acidic strength increases along the period as the electronegativity of atoms goes on increasing. Hence they will be more stable as having a negative charge on them, right, as a conjugate base. So this is more stable, hence this is the order. And if you go down the period, okay, so if you go down like this, the acidic strength also increases. Why? Because as we have discussed earlier that F minus is less stable than Cl minus, which is less stable than Br minus, which is less stable than I minus. Why? Because as we go down, the size of this actually increases to the extent that actually negative charge finds itself more suitable in a bigger size radius of the atom, right? Hence there is more dispersion of negative charge or electron within the U size of iodine atom, which actually makes the negative charge stable on iodine. On the other hand, already fluorine has very small atomic size, so between electron electron repulsion takes place, which actually decreases its stability. Hence negative charge is more stable on conjugate base, which is having more or higher size in case of same group elements, just like in this case. Okay, so now we'll be moving on comparing the acidic strengths of the compounds. Compare acidic strength. Okay, so first example is this one, this one, or this one. So we have to compare the acidic strength. So just look at whether the negative charge here would be stable or not. Are we doing it for the alpha hydrogen? No. Why? Because we have already have OH group attached on it. So this would we have to compare the acidic strengths of OH in all the cases. So would O minus charge, where will be O minus charge be more stable? So here we already have negative charge attached in all the OH groups, O minus here. So we need to compare the acidic strength of stability of this negative charge on oxygen. So as you can see that this group will be having more inductive effect. Already it is having huge inductive effect, so it would be given its electron density to the O minus, hence this would be most unstable, followed by this, then followed by this. So the order would be this. Okay, so I explained this example so that we'll be taking on our next examples quickly. But in the next examples I won't be drawing the conjugate base structure, we will be telling the stability orally. Okay, so what is the acidic strength? So what would be the impact of these groups attached to the acidic strengths? This I think I missed a CO2 here. Yeah, so here you can see it is, we are attached with a plus I group. Here we are attached with a minus I group, more minus I and more minus I. Why? Because this carbon atom has chlorine attached to it, so this becomes delta positive because of the 3 chlorine atoms. Hence this is a minus, this becomes a minus I group, this becomes delta double positive, this becomes delta positive, and it is in the giving mode. So obviously the order would be DCVA. Okay, third example, we have something like and so where is the negative charge more stable? Negative charge will be more stable. So when we see the nature of substituents to the carboxylic acid, so here the nature would be the same, that is being minus I. So how much closer the minus I group or the Br group is attached will determine the acidic strength. Hence, as I said earlier, ABC would be the order, because the Br group is attached closest to carboxylic acid in case A, then B, then C. Okay, what about this case? So in this case, you know, if you have a negative charge here, so we can see that the inductive effect of this would be more inductive effect, but the high priority should be given to hyperconjugative effect. So as we know that CH bond is having more bond length than CD bond, hence it would break up this bond quickly than the CD bond, which will take some high energy. So hyperconjugation will be more in this case. As the hyperconjugation is more, it is more plus H. As it is more plus H, it is decreasing the acidic strength. Hence, B is more acidic than A. Okay, let's look at the fifth example. We have OH and CF3 OH. So you must have a question that, I hope you have a question that, then in why case, then why the case that we are not comparing this on hyperconjugation? Why are we comparing this on inductive effect first? Because this compound has already attached oxygen atom, which is minus, which is having a minus charge already. So why would we need to compare this on the base of hyperconjugation, which will leave this carbon atom also with the minus charge, right? In this case, we had CO2 group attached. So CO2 group was something like this. So hyperconjugation was making more sense to take into the consideration because it could donate its pi electron and make pi bond. It is a negative pi bond conjugation, right? So for the condition for hyperconjugation to take place is a negative charge and double bond conjugation, just like in this case. But contrary to this needed situation, in case of hyperconjugation to happen, negative charge is not the case for hyperconjugation to take place. So it's not the sufficient condition for hyperconjugation to take place. Sufficient condition is that it should have a pi bond and a negative electron conjugate to each other for a hyperconjugation case to arise. Hence we compared it on inductive effect directly, not surpassing hyperconjugative effect. Okay, compare the acidic strength between the two. So if H goes, we have minus here and we have minus here. So this would be more acidic. The partial positive charge on carbon atom would be more here. Why? Because it is attached to more electronegative element. Hence, the complete minus I effect would be more in this case. Right? So B is more acidic than A. Let us look into this example. We have CCl3 CO2H and CF3 CO2H. So in this case, what would be the acidic strength? Same. Why? Because in this case we are only talking about inductive effect, not hyperconjugation, because there is no hydrogen atom. So where does the hyperconjugation comes into the picture? Let us take this example. We have this and we have this compound. Okay, so in this case, this rings acts as a minus M group. Why? Because d orbital resonance can take place. If we draw the structure, we have something like this, minus and Cl. So it will look something like okay. So in this case, d orbital can take place, hence is a minus M. This group is a minus M, hence it will increase the acidic strength. Hence the order would be this. But if you had gone by just the inductive effect, superficially, not analyzing the things deeply, you would have given the wrong answer. These type of questions IIT-JEE authorities just love to question you, because they know they can trick you easily. this hydrogen and this hydrogen. What is the order of acidic strength? This is greater than this. Why? Because if you look into it deeply, you can easily identify that negative charge on this conjugate base will have a d orbital resonance on sulfur. So it will result on, because sulfur has a partially filled or empty d orbital, this can form a bond with d orbital resonance. Okay, so this is more acidic. Okay, let us look into this. We have something like this and this, which is more acidic. In the conjugate base, both will be having negative charge here and here. So what is more acidic? We'll be comparing, the comparating order is ARI. We are not comparing on aromatic because we have found some other groups also attached on the phenyl ring, so it is not cyclic. Let's compare on the equivalent resonating structure. By equivalent resonating structure, I mean that two atoms on means the negative charge should be shared between the atoms which are having same electronegativity. In this case, we have two equivalent RS. In this case, the negative charge will be shared within the ring, which will give rise to negative charge being shared on carbon atom as well. So this is more stable, or this is more acidic. Okay, let us compare another good example. RCO2H and RSO3H. Which is more stable? Which is more acidic? This. Why? The same reason, d orbital resonance. Let us compare this. I explained you that day or in the previous lecture that ester is too busy with its own internal resonance. It does not care whether you have a negative charge with the adjacent or alpha carbon or not, right? So in this case, what would be the acidic strength? The acidic strength would be, as we can see, that negative charge would remain here itself, right? So it won't be getting delocalized into this or this. While in this case, it is at least having delocalization option with this ketone group, and in this case it is having a delocalization option with these two ketone groups. So what would be the order? A greater than B greater than C is the acidic strength order. So with this we end this lecture, and from the next lecture we will be seeing some more examples on comparing acidic strengths, some more good examples, some more tricky examples, and then we will be comparing the acidic strengths based on, I'll be giving you a fact based on the comparison of acids on as a factual basis. Okay, bye bye.